Welcome to qnawire.
Chapter 16, Problem 100 from Chemistry, the Essential Science. So this question is telling us that we have 0.3 grams of CaOH2 and 50 milliliters of 1.4 molar HNO3 and added to water to make a volume of 7 milliliters, 75 milliliters, and then we are wanting to find the final pH of the solution. So to do this, we're going to use an ice table, but to first do the ice table, we also have to know the general equation in which we're going to be using. So the equation we have is CaOH2 plus HNO3 goes to CaNO3 2 plus H2O. Now we have to balance our equation out, and since we have 2 NO3s over here, we're going to put a 2 in front of here. Then now we have 4 hydrogens on this side, and to make it balanced, we're going to put a 2 in here, and now our equation is balanced. The next thing to know is that since we're dealing with acids and bases, it's easier to do an ice table with just moles to be able to just subtract it out, also since we have a change in volume. So the first thing we're going to do is calculate how many moles of Ca we have, CaOH2, and all we had to do is divide by its molecular weight. And the molecular weight of CaOH2 is 74. And so when we plug that into our calculator, we get 0.004 moles of CaOH2. All right, the next step is to find the moles of our next starting reagent, which is 1.4 molar of HNO3. And we had 50 milliliters of that, so molarity is equal to moles over liters, and we are given moles in the volume, so M times L will give us our moles. One thing to make sure you know is that we are given 50 milliliters, so to get that into liters, you just divide by 1,000 milliliters per 1 liter, and therefore our new equation will be 1.4 times 0.05, and that will give us our moles of HNO3, which is 0.07. All right, so now since we have our initial concentrations of our starting solutions, we can now finish and solve our equation. But one thing also to note is that these solutions are aqueous, and then water is a liquid. Water also does not play a role in our ice table whenever we're setting it up, or in the equations of Ka when you are doing the Ka equation. So something important to note is that we are first having initial concentration or initial moles of 0.04 for our Ca, and then our moles starting off for our our HNO3 is going to be 0.07. And then we start off with 0 of our product. So what's going to happen here is a change in our solution, and the best way to be able to calculate this is by using our stoichiometry of our equation from above. If we are using all of our CaOH2, since it is our the smaller amount of our liquid, and we can tell by our limiting reagents because we already converted our moles, we are just going to then figure out how many moles of CaOH2 is needed to react with NaOH3. And so if you have 1 mole of CaOH2 to a 1:2 ratio of HNO3, you have 2 moles per every 1 mole of CO3. So therefore, we're going to have to multiply 0.004 by 2 to know how much we are losing of the original starting concentration of NaO3. So 0.008. So here we're just going to be losing the 4 moles of our CaOH, but here we're going to be losing 0.008 moles of HNO3, and then here we're going to have the addition of 0.008. So now we then write our exchange equilibrium. So then we have 0. Here we'll have 0.062, and here will be 0.008. So the question is asking what is going to be the final pH of the solution. So our H plus concentration is going to be found from our HNO3. So we only have 0.062 moles of that. So to find our concentration of our H ion, we're going to do 0.062 moles over the total volume, which we can find, which was 50 milliliters. Which they told us what our final volume was 75. We brought it up to 75 milliliters. So it's just 75. But once again, we had to convert that to liters, so we just divide by 1,000. So our molarity of our H plus concentration is going to be 0.827 molar. And then when we plug that into our pH equation, pH is equal to the negative log of our H plus. We get a pH value of 0.0